So last time we saw that f is defined as positive for a concave mirror, sometimes also called a converging mirror since it brings parallel light down to a point, and f is negative for a convex mirror, which is called a diverging mirror since light seems to spread out from a point, as we see below. What your eye would do if you were looking at this image is track these lines back to where they meet at a point. That's where your brain thinks the light is coming from, even though there's, of course, no light behind the mirror. And this point is, again, the focal point, or the focus, and it's one focal length away from the mirror, and that's half of the radius of curvature. Now, there is a technique called ray tracing that will let you analyze mirrors and lenses, and it looks at the shape of the mirror and lens and the index of refraction for the lens and Snell's law of reflection, and we trace light through whatever path of lenses and mirrors it may run into. This is a great way to do things on computer because it's a lot of tedious rules that go on and on and on. That shows in your book how to do this. I'm not going to ask you to do this because I think it's incredibly tedious and we don't need to do it. There is another way to do it, which is much more simple, and it's called the thin lens equation. So the example I give here is that finding where images are and how big they are relative to the object this way is kind of like adding vectors with graphical construction. And maybe you did that once where you drew them with a ruler and measured the angle with a protractor. It's just miserable for humans to do. So what we can do is look at the geometry involved and see in your book that the mirror obeys what's called the thin lens equation. Yes, it's not a lens, it's a mirror, but it still obeys this equation. This connects the focal length of a mirror to the object distance and the image distance of that object. And we can write it in this form, which is not too bad. 1 over f equals 1 over do plus 1 over di. Right away, we figure out where the plane mirror formula comes from. If we have a flat mirror, like in your bathroom, the radius of curvature would be infinite, since there's no curvature. So f would be infinite. That means we would get 1 over infinity. We're going to call that 0. We're going to do this where we say 1 over 0 is infinity, 1 over infinity is 0, and that would be horrible to a mathematician, but it works well enough for us. We can make these approximations because really what we're talking about is 1 over a very large number is a very small number and vice versa, and that is mathematically justified. So anyway, if this radius of curvature is huge, 1 over that is 0, and we're left with the right side of this equals 0. We can do some algebra and solve this and see the only way we can solve and get this equals 0 is if do equals negative di, like we found for the plane mirror. We could also say what happens if our source distance is infinity, so we're getting parallel light in. Well, this would go to 0, and we'd have 1 over f equals 1 over di, and another way to write that with algebra is that di equals f. That's what we found before. The image distance, which is where the light rays come to a point, is equal to the focal length in this case. So now that we know this, we can find the location of an image for any mirror with an object at any distance. There's another useful equation that tells us about magnification. How big is the image compared to the object? The variables here, we have HO and HI for the object and image height. We could do this with ray tracing and triangle geometry. We're just going to write down the equation. The magnification is defined as negative image distance over object distance, or positive image height over object height. So what does this m mean? There's a few rules we have to know. We may just have to memorize these. First, if m is less than 0, that means the image is inverted or upside down relative to the object. If m is greater than 0, the object and image are in the same orientation. If the absolute value of m is greater than 1, then we would say the image is larger than the object. But if the absolute value of m is less than 1, the image is smaller than the object. So we can put in some numbers and see what we get. Let's say we have a mirror with a focal length f is 0.5 meters and it's positive. That tells us right away it's a concave mirror. We then put an object 1.5 meters away from it. So thin lens equation, we put in what we know. Then we have to do some algebra to solve for this. We do 1 over a half minus 1 over 1.5. That's going to equal 1 over di. So we have to invert what we got to find di. And we get 0.75 meters. Now that we know this, we can plug it in the magnification equation. First, we notice this di is positive, so this is going to be a real image. We could project this onto a screen if we wanted. Now we plug it in the magnification formula. We get negative 0.75 over 1.5. That gives us negative 0.5. So what that tells us is that our image may be real, but it is inverted. It's upside down. It's also smaller than the object. As we move closer to the mirror with our object, let's say we let our object distance go to 0.75 meters. Now we do the math and we get that di is 1.5 meters. So our magnification is now negative di over do, negative 1.5 over 0.75, negative 2. The image is still real because this is positive. Sorry, this is positive. The image is still real. It's still upside down because of the negative, but now it's twice the size of the object. It is magnifying. What if we move in so that the object distance is equal to the focal length? Now we're going to have this equals this. There's nothing left for this. This has to be 0. So if 1 over di is 0, di must be infinity. What that tells us is there is no image. Parallel light leaves the mirror. The image is a place where the lines cross, and these lines don't cross till you get to infinity, so there is no image. If parallel light leaves the mirror, this would be a good design for a flashlight. You have your light source at the focal length, and you put this concave mirror behind it, and parallel light comes out of the flashlight. What if we get even closer than the focal length? So now object distance is 0.25 meters, but we still have the same focal length. When we solve for di now, we get negative 0.5 meters. That negative image distance means we have a virtual image. It will also be upright because the magnification, we now have the negative of a negative, so we get plus 2. So the image is virtual, upright, and larger than the object. If you don't have a makeup mirror or a shaving mirror that magnifies at home, you can just take an ordinary spoon and get a good approximation of this. You look into the bowl, where the food goes in the spoon. When you're far away, your image is upside down and small. As you get closer and closer, eventually you'll pass through this point, and then closer than that, you suddenly appear upright and magnified. We can now try the same thing with a diverging mirror, the convex mirror. So here let's take f as negative 0.5. And again, start with an object 1.5 meters away. We're still just doing algebra. We solve this for di, and we get negative 0.375 meters. So we know it's a virtual image. We can't project it. M is, in this case, negative of a negative, or positive 0.25. So the image is virtual, it's right side up, and it's smaller than the object. We move closer in. At 0.75 meters for an object distance, our image distance is negative 0.3. Our magnification is now plus 0.4. So still a virtual image, right side up still, and still smaller than the object, but bigger than it was. Does anything special happen at 0.5 meters? No. And the reason is the focal length is not 0.5 meters, it's negative 0.5 meters. We solve for the image distance, we get negative 0.25, so it's still virtual. Magnification is positive 0.5, so it's still upright, still smaller than the object. And finally, if we go into 0.25 meters, still get a virtual image, still smaller than the object, and still right side up. This is like a shoplifting mirror, if you want to think of it that way, the image in a mirror in a convenience store. So all the images are virtual if you just have one diverging mirror, and the image is always smaller than the object. And what does that mean? If the image is always smaller than the object when you look at it, it means objects in the mirror are closer than they appear, just like on the right-hand side of your car. It's the same thought as the anti-shoplifting mirrors. If you're trying to fit an entire store into this little tiny space that the mirror takes up, you have to make it much smaller for it to be able to fit into that space.